Okay, in the last discussion, we left off with the idea of divergent boundaries, and is the Earth getting any bigger over time? Well, we were supposed to complete the Google Earth activity where you investigated a couple of locations, the location of Tonga, the location of Chile, and California, to notice if there's a pattern to the earthquakes, a pattern to the depth of the earthquakes, and any common landforms they may have. If we take a look at this map that plots earthquake location and depth, we'll notice in several spots we have these areas, especially Tonga, where you investigated right here, where you have not only shallow, you also have medium and deep earthquakes. Again, you investigated Chile, and in this location you have shallow, medium, and deep earthquakes. And then in California, you should have noticed you have only shallow earthquakes. This is significant because they are different types of plate boundaries. Let's take a closer look. Again, these questions I want you to keep in mind as we go through. Review these, think about them, and come back to them at the end of this discussion. When you plotted the information at Tonga, what you should have noticed is you have clusters of shallow earthquakes near the top, medium depth earthquakes down here, and then these deep earthquakes near the bottom. The reason for this is you have an oceanic plate over here colliding with another oceanic plate to the west. So what happens is as these plates collide, one of them is forced underneath the other in what is known as subduction. And this subduction creates these different depth earthquakes. As this plate subducts, what it does is it drags a little bit on the other plate, creating these deep sea trenches. These trenches are the deepest trenches in the world. Above, or just to the left of this, you'll notice you have the island chain of Tonga. This results from magma forming as this plate subducts, rising to the top and creating active volcanoes. These volcanoes are called volcanic island arcs. Oops. Volcanic island arcs. This type of boundary is known as an ocean-ocean convergence. Chile, on the other hand, here would be the data from Chile, you'll notice has a very similar pattern. We have our shallow earthquakes, our medium, and our deep earthquakes. You'll also notice if you were to look at Chile, at this location here, you're going to have your deep sea trench. You're going to have active volcanoes. And these volcanoes create coastal mountain chains. In other words, mountain chains directly on the coast. Oops. This is known as an ocean-continent convergence because you have an ocean plate colliding with a continental plate. Here then is a 3D image depicting one plate subducting underneath the other. You'll notice an island chain here. This is where you'd also have your active volcanoes, like so. And you'd have your trench out in this location. So to summarize convergent boundaries, there are three types. Convergent in general means two plates colliding. Ocean-ocean convergence refers to an ocean plate colliding with another ocean plate. What you need to keep in mind is that ocean plates are more dense than continental plates. Less dense. Things that are more dense will go underneath those that are less dense. So when we get to the ocean-continent convergence, you'll see this happen. With an ocean-ocean convergence, two ocean plates collide, and one ocean plate subducts, or goes underneath, the other. And I will show you a diagram of this in 1 second. As we discussed previously, common properties or physical features of these are going to be trenches, as the one plate drags the other underneath. You're going to have a volcanic island arc, and active volcanoes. In addition, we talked about how you have shallow, medium, and deep earthquakes because one plate is subducting underneath the other. The diagram of what this looks like can be found here. So we have one ocean plate subducting underneath another ocean plate. As this plate subducts, you create your trench here. and your volcanic island arc here, because this plate begins to melt, creating magma that rises to the surface, creating that volcano. You're also going to have your shallow earthquakes, your medium depth earthquakes, and your deep earthquakes as a result of the tectonic plate subducting into the mantle. The next type of convergent boundary is going to be an ocean-continent convergence, and as you could probably figure out, this is where an ocean plate subducts, there's that word, under a continental plate. Again, the ocean plate is more dense than the continental plate, so it's going to go underneath. This would be an example of Chile that you graphed. Common properties that you saw here were trenches, coastal mountain chains, active volcanoes, because of the melting plate, and again, shallow, medium, and deep earthquakes because of the subducting plate. The diagram for this is very similar to our ocean-ocean convergence, but instead we have a continental plate here. So the ocean plate collides and subducts underneath. The continental plate forces the oceanic plate underneath. Again, here's your trench because of that drag. Active volcanoes. Again, located on the coast. Here's the ocean right here. Here's the coast. So you have your coastal mountain chain. And again, shallow, medium, and deep earthquakes. The third and final type of boundary is going to be the continent-continent convergence. This is where two continental plates collide. Neither one subducts, so neither subducts. And if they're not going down, the only way they go is up. Common features for this one. Well, first, the example of this would be the Himalayas. Tallest mountain chain in the world. In this case, we're going to have only shallow earthquakes because there's no subduction. No active volcanoes, again, no subduction. We're going to have a continental mountain chain. And typically, large magnitude earthquakes. So if we take a look at this diagram, two continental plates collide, no subduction. This here is ancient subduction from when the Indian plate originally collided with the Eurasian plate as Pangaea broke apart. But now it is currently just colliding, and the only direction for this to go is up. So you're going to have your shallow earthquakes because there's no subduction, tall continental mountain chains because it's surrounded by continent. The last type of plate boundary we need to talk about then is the transform boundary, often referred to as a strike slip. This is where two plates slide past each other. And this is not an easy movement. They're going to grind against each other, eventually building up pressure, and finally slipping, releasing an enormous amount of energy, creating earthquakes. This is what you saw in your California graph. The San Andreas Fault is a great example of this type of boundary. Typically, you're going to have only shallow earthquakes. Just like continent-continent convergence, there's no subduction, so only shallow earthquakes. You're not going to have much else. You might have a fault or evidence of a fault visible at the surface, but you're not going to have mountain formation. Again, no mountain formation because they're not colliding. They're sliding past each other. No active volcanoes because you don't have a subducting plate. Diagram for this would be something similar to this, where you have one plate moving this direction, another one moving in that direction. Only shallow earthquakes, because remember, our crust is very thin, only 5 to 60 kilometers thick. So the deepest earthquake you're going to find won't be any more than 60 kilometers. Here again is just a diagram showing a movement. Here would be that fault visible to the surface in a farm field of a transform boundary. Again, you should be able to go back to these questions now and answer each one of these. Why are earthquakes concentrated in zones? Why are there zones of only shallow earthquakes? Why are there zones of shallow to deep earthquakes? And why are volcanoes located near these medium and deep earthquakes? In our next discussion, I will summarize a complete cross-section of what all of these different boundaries look like, along with construct a tree map to organize all of this different information.